Okay, we'll continue with the third part of today's lesson. And before we go ahead, you may work and complete the questions 4 and 5 in your workbook. And you can check your answers. Now, let's start with logic that's then behind the colorimeter, because this part of the video is dealing with colorimeter. What the conservation law of energy is saying that the energy is not it is not created, not destroyed, but is transformed from one form to the other. So in the colorimeter, what is happening is that the enthalpy change of the reaction is either absorbed or released, absorbed from or released to the surrounding. So what do we have in terms of the conservation law of energy, or the way that the conservation law of energy is written in thermochemistry, is that the enthalpy change of the reaction, the total enthalpy change of the reaction, is transformed into heat of the surrounding. From the first part of the day one lesson, we know that the surrounding, the heat of the surrounding, is calculated as Q is equal mc delta T. From the second part of the today's lesson, what we know is that the heat of the reaction is calculated as the product of moles participating in the reaction times the change enthalpy of the molar change of enthalpy of the substance. So therefore, when we are combining those two with the conservation law of energy, what do we have is about the equation as N, which is the number of moles, times the molar enthalpy of the reaction, is equal to mass of the surrounding times specific heat capacity of the surrounding times the change of temperature of the surrounding. So in other words, what is saying here is that the heat lost is equal to the heat gained, and it doesn't matter which way is gained or which way is lost. Or more scientifically, all right, is the total enthalpy of the change of the system, chemical system, is equal to the total enthalpy or the heat that is the surrounding. So in other words, the conservation law of energy in the colorimeter is applied something like this. Heat lost is equal to heat gained. If the system is losing the heat, then system is losing heat, then we will have N times delta R equals to mc delta T. That means that here we have the system or the chemical reaction, and here we have the surrounding. And if the system is gaining, then we will have again mc delta T equals to N times molar enthalpy of the reaction. So depend on, here we will have the surrounding, and here we will have the system. And when I say system, is the chemical system whatever is happening in the reaction. Okay, so this is the logic that stands behind the colorimeter. So now let's see some examples on colorimeter. We have an 8.00 grams of aluminum nitrate dissolved in 1 liter of water to use as a plant fertilizer. Water is increasing the temperature from 21 degrees to 30.39 degrees Celsius. Determine the molar enthalpy of the solution for aluminum nitrate. Now, the logic is that what is happening here is that heat lost is equal to heat gained. Okay, now since the temperature of the water, the surrounding is increased, the surrounding will be gaining or will be losing. The surrounding will be gaining. Okay, therefore, this gain is coming as a result of the loss that the system is having. So that means that the system, which is n times delta RHM, is equal to the surrounding MC delta T. And we know what M is because it is 1 liter. And now we know that 1 liter is equal to 1 kilogram of water because of the density of water is 1 gram per volume. C is it's water, it's liquid. It's found in your data booklet as 4.19 kilojoules per kilogram. And then the change of temperature is 30.39 minus 21 degrees. And we are looking, so we do know all those three quantities on this side. We don't quite know the number of moles for aluminum nitrate. However, doing stoic, we will figure it out, the number of moles, because we'll find the molar mass of aluminum nitrate and then use the 8 grams of aluminum nitrate, and we are looking for the molar mass. So, the molar enthalpy change. So the formula will look something like this. MC delta T over number of moles. Okay, so now let's plug in the numbers. Uh, 1 kilogram times 4.19 kilojoules per kilogram degrees Celsius times 30.39 minus 20.00 degrees Celsius over 8 grams of ammonium nitrate that will have a molar mass of 80.06, because what do we do is we take a look at the formula on your page 4, and then you will see that ammonium nitrate is NH4NO3, so therefore you have 2 nitrogen, 4 hydrogen, and 3 oxygen. So the molar mass of ammonium nitrate is 80.06 grams per mole, which means that if you have 1 mole of ammonium nitrate, then you have 80.06 grams of ammonium nitrate, or if you have 80.06 grams of ammonium nitrate, then you have 1 mole of ammonium nitrate. So then, in order to cancel the grams, what we do is we will use the ratio 1 and not ratio 2, so that we'll have 1 mole over 80.06 grams. So grams and grams will cancel out, kilograms and kilograms will cancel out, degrees Celsius and degrees Celsius will cancel out. So the result will be into kilojoules per mole, And this is what we were expecting because we are finding the molar enthalpy of the solution. And this will be using the cup. So the molar enthalpy for the solution will be what the calculator is giving you, 435.667 and so on kilojoules per mole. This is we have to round it into 3 significant digits. So the final answer will be 436 kilojoules per mole. So we have now a 9-gram sample of charcoal, carbon, which was completely consumed by in a bomb calorimeter. If we assume that 2 liters of water is absorbed all of the heat released by the charcoal, so it is the conservation law of energy, then the temperature of the water will increase from 20.25 to 56.04. What is the molar mass of enthalpy of carbon? So what do we have here? Again, heat lost equals to heat gain. The one that is gaining is surrounding. How do we know? It's the temperature is increased. The one that is losing is the system, okay, chemical system. So now what do we have is n times the molar enthalpy is equal to mc delta T or Q, but we know from the day one, and this is the change of enthalpy of the reaction. So now what we are looking for is, this is the equation that we have to focus on. Okay. What we are looking for is the molar enthalpy of carbon will be mc delta T over N, or 2.0 liters or kilograms times 4.19 kilojoules per kilogram degree Celsius times 56.04 minus 20.25, the whole thing over 9 grams of carbon times the molar mass of carbon is 12.01. So grams and grams of carbon is cancelled out. Kilograms and kilograms of water is cancelled out. Degree Celsius and degree Celsius are cancelled out. So what we have here in terms of the units is the kilojoules per mole, which are the units that we were expecting. Then after you plot it into your calculator, you will find that it is 400.226 kilojoules per mole. However, the final answer have to be expressed into 2 significant digits, because the lowest number of significant digit is 2 versus 4 that we have for temperature. So then the final answer will be 4.0 times 10 to the power of 2 kilojoules per mole, expressed into scientific notation form, because we want to express it into 2 significant digits. And this will be the molar heat of carbon. Okay. On the slide, we have 4 methods of communicating enthalpy change, but before we go there, I want to complete a question on neutralization before we do that as the third part of our lesson today. Okay, so this will be the an example of neutralization area enthalpy calculation. 25 milliliters of 0.5 molarity of sodium hydroxide and 25 milliliters of 0.5 molarity of hydrochloric acid are mixed in a calorimeter, and the temperature of the resulting solution is increased from 25.00 degrees Celsius to 28.25 degrees Celsius. Calculate the molar heat of reactions in kilojoules per mole, and we can do it for any of the reactants. Yeah. So now the very first step is we will write a balanced chemical reaction. So what do we have, if you remember from even the review that we did at the beginning of the course, where a base and an acid are reacting together, then neutralization is happening. So sodium hydroxide in aqueous solution is reacting with hydrochloric acid in aqueous solution to produce water and salt. In this case, sodium chloride as an aqueous solution. Okay. Now, this is a balanced equation because we have one sodium hydroxide, oxygen 1, 2 hydrogen, and 1 chlorine. So this is balanced equation. So the assumption that we are doing here is that the volume of product is the combined volume of the reactant. And the other assumption is that the aqueous solution, or liquid in our case, is the same as product. I will say here, products will be considered as water. Consider as water. And what do we do for water? We pick the specific heat capacity of 4.19 kilojoules or joules per kilograms or grams degrees Celsius. So those are the two assumptions that we do here on this case, and then we start solving it using some knowledge from the solution unit on chemistry 20. So the concentration for each of them will be 0.5 moles, which molarity is moles per liter, okay, and 0.5 molarity. Volume of each of them, we said, is 25 milliliters plus 25 milliliters, which will be the volume of the product, which in this case will be 50 milliliters. And this will be the same as saying that we have water of 50 milliliters. Okay? Okay, good. So now we start and solving it using the conservation law of energy. So heat gain is equal to heat lost. What is gaining is the surrounding, or is on the product side, and what is losing is the product, the reaction, the chemical system. So now what is gaining is considered to be water. So will be Q equals to MC delta T. And what is losing is the enthalpy change, okay, number of moles times. And this is neutralization molarity, okay? Enthalpy, molar enthalpy of neutralization. Okay, so now we have mass here as equals to 50 milliliters, which is the same as saying 50 grams. We've said it because the grams and moles into the water are the same. C is equal to 4.19 joules per gram degree Celsius, and delta T will be whatever is the final minus initial. So in our case, will be 28.25 minus 25. So the change of temperature is 3.25 degree Celsius. So we have the heat here. We are able to calculate the heat. Let's move to the other side here and calculate the number of moles using the fact that we know the volume and the molarity of the substances. So now if we focus on let's say, sodium hydroxide, because this is a 1-to-1 ratio, but it is the same logic as if it is not 1-to-1. So if we take a look at the sodium hydroxide, what do we have here is a 1, 1, and then the rest of them is 1 as well. So if we start with a volume of sodium hydroxide, then we will have something like this. So 25 milliliters of sodium hydroxide times, let's convert this into liters first. So we'll have 1,000 milliliters is a 1 liter of sodium hydroxide. So sodium hydroxide and sodium hydroxide, milliliters of sodium hydroxide is cancelled out. Using the fact that we have a molar concentration of 0.5, then we will say that in 1 liter sodium hydroxide, we have 0.50 moles of sodium hydroxide. So 1 liter and 1 liter of sodium hydroxide is cancelled out. So this one gives us the number of moles of sodium hydroxide, and in our case, the molarity of the reaction is that 1 mole of a reaction is 1 mole of sodium hydroxide. But if it is a different one, like in the case of let's say sulfuric acid reacting with sodium hydroxide, then those will cancel out. So this will be for the reaction. Okay, reaction. So now when you enter in your calculator 25.0 times 1 times 0.5 over 1,000, then what you will have here is the number of moles of reaction. But you can stop at the number of moles for sodium hydroxide as well, is 0.0125 moles. So in this side of the given, what we have is 0.0125 times the neutralization, change enthalpy of neutralization reaction, molar of it. So now that we have the two sides of the equation, we can go ahead and figure out what is the molar enthalpy, the change of molar enthalpy of the reaction. So neutralization, change of enthalpy, molar change enthalpy of neutralization will be equals to 50 grams times 4.19 joules per grams degree Celsius times 3.25 degrees Celsius over 0.0125 moles. So the answer will be 54470 joules per mole, or if you write it into kilojoules, it will be 54.470 kilojoules per mole. Now let's take a final look into the significant digits, and I notice here that significant digits are 2. So we can, the final answer will be the change of enthalpy, molar change of enthalpy of the neutralization will be 54 kilojoules per mole. Sorry about that noise. This is what is happening when you record the lessons in an environment that is not quite great. Anyway, this will be the neutralization, and now we are finding it, since it is one-to-one, is the same thing, but if it is a specific one, then we will see what is the molar enthalpy of, let's say, sulfuric acid. We'll do an example in class. It's very similar to that. This concludes this part of the lesson for today. And we will go to a very short one, in which is the ways of displaying the enthalpy.